Hello, Callie. Hopefully I can make a few videos to help you with your questions that you had. Let me make sure my drawing's working first. All right, perfect. Let's undo that. Okay, so the first thing I would do is encourage you to watch the videos I posted in Blackboard because I noticed that some of the questions you asked were directly related to those videos that I posted. So those will help a lot. But let's walk through these. So here's the first thing we're going to do. This first question you asked about is the epsilon delta definition of a limit. So the first thing you want to know is what that definition is. And basically, I'm not going to go through the whole thing, but you'll want to look it up in the textbook in section 2.2. And basically what it says is that if you have the difference between the function, the height of the function, and the limit, you want that to be very small. And the way we say that it's very small is that we say that it's epsilon. As long as, so really what this means is that the function is very close to the value of the limit of the function. Because the difference, the distance between those two, which is what f of x minus L represents, is less than epsilon, right? So the distance between the function and the limit is less than epsilon, and epsilon just represents a very, very small number. As long as, and the other thing we want to be true is that we want x to be approaching 9. So we want x to be very, very close to 9 in this case. And so we say that x minus c, and c is just a general value for where that could be approaching. In this case, it would be 9. We want to make sure the distance between those is also very, very small. So we're going to say that that's less than some other very small number, delta. And we want to make sure that these two things are related to each other. So to translate this first part into the example we're using, we would say the distance between the function x plus 8 and the value of the limit. So we have to evaluate the limit. You know the value of the limit is 17 because you plug 9 in here, right? So you get 9 plus 8 is 17. So we say the distance between the function and the limit, 17, is less than epsilon. That has to imply that x is very, very, very close to 9. We want this to imply that the absolute value of x minus 9 is less than delta, some small number. So the way we do that is we kind of just reduce this. So you can see pretty easily that this translates to, in this case, 8 minus 17 is just negative 9. So this shows the relationship that we want to show. Basically, in this one short step, we've showed that if x is very, very, very close to 9, then the function has to be very, very, very close to 17 because these are really just the same statement. So that's the work you'd want to show on test for that one. This one's a little bit different. Here they just wanted you to fill out the table. So the easiest way to do this is just to put the function in the calculator. You could just calculate these things one at a time, but it's easier just to put it in the calculator. So I'm going to put in parentheses and then do the absolute value, which is in number here, the absolute value of x plus 5 minus the absolute value of x minus 5, and all of that over x. If I graph that function, oh, my zoom is a little messed up. Let's do zoom standard. That should show it, I think. And we're doing this as x approaches 0, so yeah, this is perfect. I can actually zoom in a little bit. We can see that we know that it approaches 2 like the answer you got. But to do this by hand, you would just estimate it by picking values that are closer and closer and closer to 0. So we've done ones like this before. You could make a little table. Here's x. Here's f of x. And we're going to make a table of values. Maybe I'll do 5. And here would be 0 because x is approaching 0. But we can't put 0 in, right? So this would really be undefined here. So that's supposed to be a question mark with my beautiful handwriting. But we can go ahead and trace at different values. So I want to be very, very close to 0. So maybe I'd choose, I don't know, I'm going to trace at, let's see. Let's just do 0.1 to start. And at 0.1, x is equal to 2 already. So at 0.1, maybe I'd put that here, 0.1. When x is 0.1, y is 2. And when x is 0.01, y is 2. So when x is 0.001, so 0.01 and 0. So I'm just filling in the table. I also get 2, right? And then you could do that from the left as well. So I could put in negative 0.001, and I also get 2, negative 0.001, and etc. You can see that it's going to be 2 no matter what, but I'm going to plug in negative 0.01 also, just for one more example, negative 0.01, and I also get 2. I'm not sure if I did negative the time before, and just to do it, I know what it's going to be, but just to do it, there's the other one that comes out to be 2. So that's how we know that that limit's 2. For not all, you can't use this kind of technique unless the question tells you to. So by evaluating f of x at x values near 0 tells you that you can use this table method to do it. But if it doesn't say that, then you have to do it analytically like other limits we have done in chapter 2. So for this one here, let me make this a little bit bigger as I can't really see it. Oops. Just want to make this bigger for us. Won't let me move it that way. But this is the same kind of problem. Yeah, this exact problem is posted in the in Blackboard on my YouTube channel. So make sure you watch those. But just like the first one we did, you want to start with f of x minus L, oops, that's a big minus, is less than epsilon, and you want to get to, from there, you want to get to that f of x, that x minus c is less than some value delta. This one's a lot harder than the previous one because it doesn't just fall out. But f of x in this case is x squared plus 4. That's just the function we're dealing with. The value of the limit is L. You already found that. It was 29. And we start with the fact that that's S and epsilon. And so from here, you kind of just follow your algebra nose. You know you can simplify this to x squared minus 25 is less than epsilon. Then since you're a good algebra student, you look at x squared minus 25 and your first instinct is, oh, let's factor that. And so I can do x plus 5. I apologize for my handwriting with this program. It's not very good. X minus 5. And I just did something with those absolute values that we don't often do. It's not natural for people to do it. But just keep in mind that it's true. If this value is always going to be positive, and I split it up into these two things that are being multiplied together, but are always positive, then it'll come out to be the same value, right? So it's going to be positive on this side no matter what. So that's something you can do with absolute values, is split it up like that over multiplication. So we're pretty close to where we want to be. Keep in mind our goal is to get to x minus c, and c is the value that x is supposed to be approaching, so it's x minus 5, right? This is where we're trying to get. We want x minus 5 to be less than some value of delta. Oh, it looks like you got the right answer. I'm going through this whole thing, and now I've just noticed that you've got epsilon over 11. The only problem with this is, I should have noticed this right in the beginning. The only problem with this is you can see, I'm going to change colors here, that in the definition they use epsilon, but WebAssign instead of epsilon was using this 0.01. And that's because WebAssign wants to look for a number instead of looking for an expression. It's easier for WebAssign. So instead of epsilon over 11, which I just noticed is actually the right answer if this was epsilon, you just substitute 0.01 for epsilon because WebAssign had done that, right? So you put in 0.01, and this is why they're asking you to round it to a certain number of decimal places. I think it says 4 decimal places there, right? So you put 0.01 divided by 11. I'm just going to do that on the calculator real quickly. 0.01 divided by 11, and I get, okay, that's 4 places, so 0.1, 2, 3, 4. 1, 2, 3, 4, yeah, that's what it is. So 0.00009, you want to round that, well, the next digit is 0, so that would be the answer that they're looking for. So the good news here is you were doing it right. You were just following my instructions and how I did it with epsilon. Just with WebAssign, you'd use this number. Actually, on a quiz or a test or our midterm exam, you'd just use epsilon over 11, and that would be fine. Oh, you're not taking a midterm. Your section, I'm sorry, that's a different section I'm talking about. Yeah, but your section, you won't need to do a midterm, just on the final. That's how you'd want to show your work. Okay, so this one, 17, we're trying to find this limit. Oh, there's a little trick to this one. So we're doing the limit. If you don't mind, I'm just going to write limit here, and we'll just know that it's the limit as x approaches 0. That'll just save me a little bit of handwriting. The first thing I'm going to do with this is I'm going to factor out the 6 from the numerator. So it leaves me with 1 minus e to the negative x all over e to the x minus 1. And these are close, but these don't really cancel out in any way, right? Because of this negative x, these would be opposites if that was just e to the x up there, but they're not, right? This 1 minus e to the x and e to the x minus 1 would be opposites, but this is e to the negative x. So the little trick we use to do that, I'm trying to think, oh yes, so we multiply the denominator by e to the negative x and the numerator by e to the negative x. It's just a little trick. And you'll see what happens. So I'm just going to leave the e to the x factored in the numerator. In other words, I'm just going to write it, the limit, and I'm not really going to multiply through. I'm just going to leave it 6 times 1 minus e to the negative x, and leave this e to the negative x out here. Whoops, let me make that a little bit smaller. E to the negative x out here. But in the denominator, I am going to multiply it through. So I'm going to say e to the negative x times e to the negative x. Well, that just turns out to be 1 because you add, there are two expressions with the same base, e and e. You just add the exponents, you get e to the 0, and e to the 0 is just 1. And then 1 times e to the negative x is just minus e to the negative x. And now you can see why I left this e to the negative x and I didn't multiply it through. It's because I wanted to find this common factor, right? Now both of these have this, oops, I wanted to change color there. Let's change color, please, thank you. I want to cancel that and that out, right? Because they now share a common factor now that I multiplied by this. So it becomes the limit as x approaches 0 of 6e to the negative x. And now, see, the problem in the beginning, just to reiterate this issue, the problem in the beginning is you can't just plug in 0, right? Because when you plug in 0, this e to the x becomes 1, and 1 minus 1 is 0, and that is indeterminate. It doesn't tell you whether or not the limit exists. But now that that factor is gone away in the denominator, I can plug in x equals 0. So this limit will be equal to 6 times e to the 0, which is just 6 times 1, which is just 6. So the value of this limit should just be 6. And again, your calculator can help you. You can't solve these by using the calculator, right? This is one of those analytical ones where you have to show this kind of work to get the answer. But if I graph this, it will help me see if I got the right answer. So I'm just entering this function into my calculator, e to the, I need a caret here, e to the negative x. And then divide all of that by, in parentheses, e to the x minus 1. And if I graph that, oh, my window won't show it, so I'm going to pause that and change my zoom to zoom standard so we can see it. It'll take this one a while because this virtual calculator has a hard time evaluating things, but you can see, sort of, that at 1, 2, 3, 4, 5, 6, let me change the window a little bit so we can see it. So let me go from x equals negative 1 up until, let's say, about 8. And to zoom in for the y's, I'll go from negative 2 to about 2 because we wanted to zoom in. Oh no, that won't do it. Let's go from negative 2 to about, oh, I meant this one to be negative 2 to about 8, and the x to be from negative 2 to 2. That's what I meant. Graph that. And you can see what happens at x equals 0 pretty well. You can see now that it's about at 1, 2, 3, 4, 5, 6. So again, I'm not trying to get the answer with the calculator, but this graph definitely verifies that limit might be equal to 6. Again, using the method we used before, if you use numbers that are very close to 6 for x, very close to 0 for x, 0.001, you'll get something that's very close to 6, and negative 0.001. Again, something very, very close to 6. So that just verifies that that limit really is approaching 6. Oh, and that's all the questions. Did I get them all? 1, 2, 3, 4. Yeah, I felt like there was more. Well, I hope that works. I'm going to hopefully, because this file is going to be way too big, I'm going to set this up on my YouTube channel so that you can see it. I hope that helps.